All right, so in this lecture, we're going to talk about glaciers and glaciation. And this is a process by which much of the land in both higher elevations, like in mountainous regions or alpine regions, as well as lower lying flatter areas on the continents, this is the way that much of this stuff has either eroded or carved out, or else large amounts of sediment can be moved around and deposited. And much of the landforms that we see on many of the continents, if not all of the continents, is heavily influenced by the act of glaciers and glaciation. So I want you to take a minute to look at this shaded relief map, or sometimes called a grayscale elevation map, of the Western Great Lakes. And I want you to notice a few things. These smooth troughs here that we see carving through the land of much of northern and western Wisconsin, as well as Minnesota. And also a lot of these curved ridges and things that you see kind of perpendicular to the direction of the lake here that run sort of east-west. So what do you think caused these smooth areas? And I want you to think, is this process that formed these things still continuing today in these areas? And similarly, we have, again, these curved ridges, and you'll notice that they follow a sort of topography here, and you can see all sorts of different features here. When we take a sort of holistic bird's eye view look at the Great Lakes region. And the feature that's maybe most conspicuous is just the fact that we have so many lakes, and the largest lakes on the planet for the most part. And I want you to think, what are these features, and what do they tell us about the geologic history of this area? Well, if you guessed glaciers, you're right. So during the Pleistocene epoch, which lasted from about 1.1 to 1.2 million years ago until about 50,000 years ago, glaciers covered as much as 30% of all land surface, as seen over here in this figure on the left. And today, glaciers cover about 1/10 of the land's area, primarily in Greenland, and if we were to spin this around, down there in Antarctica. And there's lots of evidence left behind by glaciers as they both carve into the land and deposit sediment. And here are some features we're going to look at in this lecture and in lab, in an alpine setting, and then depositional features and things that we see on the continent, and effects that glaciers have on existing bedrock, and how they've shaped on a massive scale much of the surface area of the land that we see today. So as I've said before, glaciers store over 75% of all fresh water on the planet. They, over geologic history, have produced many of our high-yield aquifers. And like I talked about in groundwater, there's lots of groundwater that's being stored in the subsurface. And while much of that is precipitation in many areas, a majority of our high-yield, very sustainable over time aquifers are from glacial meltwaters. They produce much of our arable land, and arable means fertile and able to farm, able to grow crops on. And glacial meltwaters provide domestic water, as I've said, and also water for hydroelectric energy. So glaciers are two things. They're dynamic features capable of eroding, transporting, and depositing massive quantities of sediment. And they're often found at higher latitudes, so further from the equator, and at higher elevations, so vertically further up from sea level. And there are two main types of glaciers that we're going to focus on in this class, and they are valley or alpine glaciers, shown here on the bottom left, and ice sheets or continental ice sheets or continental glaciers, shown over here on the right. And this is in Antarctica, I believe. So let's begin by defining valley glaciers. So a valley or alpine glacier is a glacial system found in mountainous regions. And quite simply, it's just a stream of ice that's driven by gravity to flow down a valley, hence the name Valley Glacier. And here's a beautiful example of one here. And we'll talk about some of these features that we're seeing here as well. And here are a couple of awesome examples of valley glaciers. You'll see up here on the top of this mountain here, we've got a bunch of snowpack, and this is called the zone of accumulation, which we'll talk about. And then we can see multiple valley glaciers flowing down through these U-shaped valleys. And it doesn't flow like water. It can flow just a few centimeters a day, sometimes meters a day, sometimes faster. But these aren't things that you necessarily see flowing past you like a river. And I'll talk more about how glaciers flow. But I just wanted to show you that you can get multiple valley glaciers kind of coming down from one single source, or you can have a really large valley glacier that's just sort of exploiting one really large valley between mountains, almost, is what it looks like. Maybe sourced from one single zone of accumulation or one area of snowpack. And then we have ice sheets, which are continental ice sheets or continental glaciers. But don't be fooled, glaciers can only form on continents. So this term continental ice sheet is really referring to the glaciers that appear on land in these giant sheets that aren't alpine glaciers. So they're not the small valley glaciers, smaller valley glaciers that we see on the previous slides. These are ice sheets that can cover thousands and thousands of square kilometers. So like I said, glaciers always form on land, and it's the amount of snowfall in the winter versus the amount of snow melt in the summer defines how a glacier forms. So you have to have more snowfall in the winter than snow melt in the summer to produce a glacier, plain and simple. And these conditions are most common at higher latitudes. Think northern United States, Canada, Northern Europe, Siberia, Greenland, and then think Argentina, Chile, like Patagonia, places like that, Antarctica, so southern far latitudes. And the way glaciers form is as there's more snow accumulation in the winter than melt in the summer, the snowpack begins to increase. And as snowpack begins to increase, the pressure also increases, changing regular old snowflakes here into eventually firn, which is a coarse granular snow. Think like almost like grains of sediment, but really tightly packed snow, okay? And there's a process in the middle of that where you get this kind of granular snow, but eventually firn. And then when that gets packed together, that's when we get glacial ice. And as we continue accumulation and increased pressure, the trapped air is expelled and the firn recrystallizes again into this glacial ice, forming this dense blue ice. And this is what that looks like. So this is an iceberg that was calved off of a glacier. And calved means just falls off into the ocean at the boundary where the continental glacier is near a large water body. And here you'll see that real distinctive blue glacial ice. It's quite beautiful. So how glaciers move? Well, once the ice reaches about 30 to 50 meters thick, it begins to flow in response to gravity, where the upper portion of the glacier and the lower portion of the glacier begin to flow down gradient, right? Down slope, even if the slope is incredibly shallow. Would almost seem flat to us if we were standing on it. And just like the crust, the continental crust, when you go lower into the glacier, just like going lower into the crust, there's enough pressure there that things begin to act like a plastic, and that's where we get plastic flow. In rocks, it's heated up and under pressure, so it acts plastically. Here, the glacier's not heated up at the lower portion because it is ice, but the pressure causes it to behave plastically. And just like the crust in the upper portion, there's less pressure, and things tend to fracture more brittly. And in the vernacular of glaciology, we call these crevices, or if you're fancy, crevasse. And one thing I want to mention here is that the speed of a glacier is not uniform across the whole glacier. And this is a graphic from the Rhone Glacier in Switzerland. And similar to rivers, you'll remember from running water lecture, the center of the river, or in this case the glacier, that's furthest away from the frictional effects of the valley walls and floor, or a river channel, like in a running water system, you'll have ice moving much faster at the center than at the sides closer to the valley floor. And here was an experiment done with some stakes in 1874. They placed stakes straight across the glacier this way. And then in subsequent years, we start to see the center stakes closer to the middle have a much higher velocity than the stakes over on the side. And as that continues, we see the same process occurring, where the center portion of the glacier is outpacing the sides. One thing to point out, and we'll talk about this again in a little bit, here's the terminus, or the end of the glacier. That's the area to which the ice is flowing. So it's usually, it's the kind of like almost the mouth of the river, so to speak, in a river system. But this is the area in which the glacier is flowing, and it terminates at this rounded edge here at the end. So I want you to think, whenever I say terminus, I'm talking about the end of the glacier as it's flowing forward, so the part that's flowing forward. And then anything on the sides we usually call lateral, which means side. So this would be the lateral side of the glacier. And here's the terminus in 1874, and here's the terminus in 1878. So the question here is, if the glacier is always moving forward, how can the terminus be retreating back? And more on that in a bit. And again, here I'll say very quickly, glaciers can move a few centimeters a day to as fast as 8 to 10 meters per day, so 30 feet a day. You could still outrun it, but that's pretty good. And it can surge up to speeds of about 100 meters per day, or 300 feet per day. You could still outrun that, but you would be able to visibly see this ice moving, see it flowing. So let's talk a little bit about a concept we call the glacial budget. And I'll begin by pointing out a few things. So this is kind of the main terminology that we use when we're talking about glaciers. And at the very top, where the snow is accumulating, we call that the zone of accumulation. So this is higher altitudes, so further above sea level, so higher up in an alpine setting or a mountain setting, or at higher latitudes in some cases with continental ice sheets. This is the area where there's the snow, and there'll be the snow line. So this is snow that's not under pressure, because it's snowing up here in the winter and sometimes in the summer even. And past that snow line, you've got this area here, and this is where the ice is under a ton of pressure, and the ice is flowing down this way under that pressure, okay? And once we get to areas of lower pressure, then we get into the area where all the crevasses are, but the ice is still flowing this way, and then we get to the very end at the terminus here, and this is called the zone of wastage. This is where ice is melting. And this is where we can get icebergs calving off from the calving events. This is where we get different sorts of glacial features that I'll talk about a little bit later, like kettle lakes and stranded icebergs and things like that. And if the rate of glacial advance is equal to the rate of wasting, then we say that the glacier is stationary. Now, I don't mean advance of ice. Ice is always advancing to the zone of wastage from the zone of accumulation. That ice is always moving this way, right? But if the amount of snow moving that way is equal to the amount of snow melting, then the terminus of the glacier just sits there. It doesn't retreat and it doesn't advance, okay? And as you can imagine, if there's more advance than wastage, the glacier will advance, right? So if there's more stuff accumulating here and moving down faster than it can melt at the end, the glacier will continue to move in this direction. The terminus will. And if the opposite is true, then the glacier will retreat. But keep in mind, again, if if the terminus is retreating or if the terminus is moving forward, we say that that's the glacier flowing forward or moving backward. But keep in mind that the ice within the glacier is always moving forward, okay? And if that's confusing, I've provided a few videos here for you. So go into the lecture slides without audio and go ahead and click on these links and have a look, and you can see what this looks like. Again, if the ice is always moving toward the glacier's terminus and also towards the margins to some extent, right? Moving to the sides, okay? And that's regardless of whether the terminus is advancing or not. So what is a glacier made out of? Well, it's made out of, like we've talked about, ice, but it's also made out of large quantities of meltwater and large amounts of rock debris. And that could be large rock debris or smaller sediments. And these are scraped off of the underlying formations. So you can imagine these glaciers are moving through mountainous areas, rocky areas. And as they do, they scrape pieces off, and those pieces get incorporated into the glacier, and then they flow down the glacier along with the ice, okay? And for alpine glaciers, they tend to erode some of the more beautiful features that we see in mountains. And this is a big solid hunk of granite. This is in Yosemite. I believe this is Half Dome. People actually climb up this guy on the side here. And this is the result of some kind of glacial erosion in an alpine glacier or a valley glacier setting. Because remember, I said valley glaciers tend to be more erosional, and continental glaciers tend to be more, or continental ice sheets, I should say, tend to be more depositional. So let's talk about how glaciers erode the land. So glaciers erode land through a couple of key processes. So one is called plucking, and this is where a glacier loosens and lifts big blocks of rock. And they can be the size of trucks. They can be the size of a basketball. Doesn't matter. Glaciers are capable of moving huge rocks. In fact, if you look in people's yards sometimes around town or in your town or in your neighborhood, sometimes you'll see huge rocks sitting in the middle of somebody's yard. I mean, something that they could never have moved in there. This is usually because the people that came and broke ground when they were building came across one of these glacial erratics buried in the till, and it's too expensive and too heavy to move out of there, so they'll just kind of landscape the yard around those giant boulders, maybe sometimes the size of a car. And this is the type of material that glaciers are capable of moving. So plucking happens by, again, glaciers form in a freeze-thaw sort of environment, right? They form in an environment where it's summer and it's winter, and the ice is moving, and sometimes in the summer, portions of the glacier will melt, and not like whole parts, but there's water in the glacier from melt, and it makes its way down into the cracks and crevices of rocks. And then when it freezes in the winter, ice expands. It's one of the only things on the planet that when it's in its solid state, it's less dense than when it's in its liquid state. And so as you have these freeze thaw cycles, you get expansion and expansion and retraction of these cracks, and eventually it will break these rocks free. This is the same way that our roads here in Michigan get destroyed over such short periods of time, because we have a lot of freeze thaw. And so water runs down into the cracks in the road, it expands and pries those cracks open. And that's why we're always doing road work here in Michigan. And once that big boulder has been plucked loose, the glacier can incorporate that boulder into its ice flow and move that boulder towards the terminus, similar to the other ice and debris that it's moving. And then glaciers also erode through abrasion. And this is where the glacier is just scraping across rock like sandpaper. And it's not just the ice, remember. In fact, it's probably not the ice that's producing what we call striations, which are just stripes, and I'll show you some in lab, across the rock surface. It's actually probably the debris, the boulders and the rocks and all that other stuff that's at the base of the glacier. That's the stuff that is most likely scraping the bedrock that the ice is moving through. So the landforms created by glaciation in an alpine setting, we have, so this is unglaciated, right? So this is just a river. And like we talked about in running water, rivers produce these V-shaped valleys. But when there's glaciation, that same valley can come to look like something like this, where ice has now exploited that unglaciated river valley, and it begins to form this really huge glacier that's moving down through the central part of that valley. We call that the main glacier. And then we have these kind of secondary glaciers over here that are running down into it, kind of like tributaries running into a river. And for valley glaciers, these are some of the features that we tend to see. So as the glaciers widen and deepen in the valley, they melt. Eventually, they create what we call a U-shaped valley, right here. And you can see those in some of the pictures earlier in the lecture. And then we can also get these bowl-shaped valleys at the head of a glacier, or at the zone of accumulation of these smaller glaciers. And these are called cirques. And here's a cirque here. There's a cirque. Here's a cirque here. Maybe there used to be one right up there. And those are kind of bowl-shaped valleys at the top of these smaller U-shaped valleys. So here's a cirque. Here's a person standing in a cirque. So this is kind of a big bowl. And then there's a smaller U-shaped valley running down into this much larger U-shaped valley that was once the main glacier. So we're up on some little side glacier, and this is the cirque. So they're huge, but that's what they look like. Here's another cirque. I've been in one of these in Colorado when there was an active glacier down in the bowl here, and we were kind of hiking across the cliff there. So another example of a cirque. And it would have been eroding this mountain away right here. All this stuff that's facing us here would be eroded away. And you can imagine if when another glaciation happens here, all this loose debris that's sitting here and all the stuff that's eroding off of this into these talus slopes, that stuff's all going to get incorporated into that glacier and carried around. And so aside from the U-shaped valley here, we see a number of other features in alpine glacially eroded regions. And the first two I'll draw your attention to are in direct relation to the U-shaped valley. So as that main glacier is moving down through the kind of winding mountain valley that the river was originally in before it was glaciated, you get these things here called truncated spurs. That's these kind of triangular shaped, sometimes maybe almost square shapes here. And this is where the glacier just carved out whatever these ridges were going down to do. It just carved those out. And those are interspersed with this other feature that we call hanging valleys. And they're smaller tributaries that don't cut a valley all the way to the U-shaped valley floor. So they don't cut as deep. Because remember, these glaciers were just flowing into the much larger glacier at one point. And so they didn't erode down into this portion here. And so once you have streams running down that, after everything is melted, they flow down this kind of smaller secondary U-shaped valley, excuse me, and they run down into a waterfall that will then run into the main valley, okay? And this is very common with a main glacial trough. You'll have U-shaped valleys, you'll have hanging valleys cutting across these truncated spurs here. So here's a U-shaped valley where the glacier, we're in the main trough here. This would have been the main glacier. It would have butt right up against this. This would have all been ice all the way across the valley. And then there was a secondary glacier running into that. And now today there's just a stream running into this beautiful waterfall here. And here's another one. So here's a lake in a cirque, basically. This is a type of lake that I'll get to, and that's a hanging valley as well, running down into this once main glacial trough that it looks like has now been inundated with seawater. So these are you've probably heard of fjords. So that's what this is. So that's where you have glaciation and then sea level rise filling in the main valleys. Those are fjords, and so this is probably in Norway, if I had to guess. Some other landforms that form after the glaciers have melted and leaving behind the eroded remnants, we get depressions within the glacial trough, where there would have been just little depressions based on the irregularity of the glacier as it ran down. You'll just get these little depressions here and there. And if they're connected in this way, right, with a stream running from that one to that one to that one and then down into a hanging valley, these lakes are known as paternoster lakes, okay? You can also get a lake that's sort of isolated from any kind of a valley, and it just kind of sits by itself in this little area up here that was once a glacier that was, this was a cirque, I guess, but different than cirques that run down this way. This would have just been sitting up there, and we call this a tarn. And it can either be in a bowl-shaped trough or it can be in a cirque. And the tarn is the name of the actual lake, okay? And then, like I said, if you have a glacial trough that's been submerged below sea level in this main glacial trough here, then we call that a fjord. Here's a fjord again. So this would have been a main glacial trough. Here you've maybe got another big glacier that was running into it here. Not quite a hanging valley because this one was pretty big and eroded down. But you can see that this is all inundated with seawater. If any of you have watched that show Vikings, that town that they all live in, Kattegat it's called, that sits at the very end of a fjord. And I think probably Vikings built a lot of their cities at the end of these fjords because then they'd be able to funnel any enemies that were kind of coming in. They'd be able to it'd make it harder for them to attack at one central point there. So a little Viking history there in addition to Earth history. Then we also have peaks formed from alpine glaciers, and there's a number of those. So when the glacial erosion cuts into these kind of knife-shaped edges, so here's your truncated spur, right? And if you go up that truncated spur, you can see where the glacier was eroding on this side and the glacier was eroding on this side. And then you had a glacier eroding over here on this side. You get this kind of knife edge, and we call that an arete. Or it might be arete, but I've always heard it say arete. You can call it whatever you want, as long as I know what you mean. And that's this knife-edged point here, or long ridge, rather. And then if you have a sharp pyramid-like peak, usually at the top, then you get something like this. And this is where you have glaciers on 3 or 4 sides. and it creates this kind of pyramid shape as those glaciers were eroding into this. We call that a horn. This is the Matterhorn in Switzerland, very famous. It's also the street I live on. And so the Matterhorn is a horn. So there would have been glaciers on all four sides of this at one point. And so it leaves behind this kind of little peak here. And here's maybe a horn or a couple of horns, and here's some aretes too. This is an arete running down. So a horn is like, you got to think of it like a pyramid shape, but if it's a ridge at all, then it's an arete. And here's a whole clump of different, there's an arete there, there's an arete over here, here's a horn, there's a horn, there's a horn, there's a horn. So this has all been carved out by those smaller kind of tributary glaciers higher up, right in the zone of accumulation. And here you can see, here's a glacier moving down right through here. And here's our snow line. Here's our zone of accumulation. That stuff's getting packed down into ice, and that ice is flowing down this valley over here. And similarly over here. So take a second. I want you to count how many glacial features you can find in this landform model. Not just, I've pointed out what they are here, but I want you to count how many of the individual ones that you see. And so for glacial deposits and the sorts of features that we see, the material that glaciers tend to deposit, we call glacial drift. And that's a general term for all sediment of glacial origin, anywhere that you find it. And there's two distinct types. So any material that's directly deposited by the glacier, so it was being picked up and carried by the glacier, and then when the glacier melted, that sediment was deposited directly right where the glacier melted. That's called till. And it's characteristically unsorted, different from what we see in river systems where the strength of the current will carry different sediment based on the grain size of that sediment. Here it's unsorted because all of the debris and rocky material is being carried by the glacier equally. And this unsorted mixture is usually, till is usually like sand and gravel and muds. But it can also be include those erratics that I was talking about that people put in their front yards, or leave in their front yards, I should say. And those are generally much larger, so maybe a square meter in surface, or a cubic meter and larger. So maybe the size of, sometimes the size of a Volkswagen or something like that, maybe even bigger. And then also you can have sediment that's laid down by the glacial meltwater. And this tends to be sorted because that meltwater does form little streams, like I showed way back in one of the earlier slides, where at the terminus there you could see a bunch of little streams coming off the edge of the terminus and running downhill at the end of the glacier there. And so those are going to, that current of that stream is going to act on the sediment and sort it based on size and weight. And this is also sand and gravel, and then finer particulates. So it's not going to move the erratics as much. It's going to move, the much finer particulates. So here's someone standing on a big pile of glacial till. This is all glacial till being left behind. So you can imagine, I mean, the volume of material that glaciers deposit is enormous. In fact, the reason Michigan doesn't have bedrock and mountains and things like that exposed is largely due to the effect of glaciers. The glaciers were plucking and eroding in areas of higher elevation in Michigan prior to the Pleistocene. And then when all the glaciers melted, it deposited all of this material. And so most of Wisconsin, Minnesota, Michigan, northern Indiana, northern Ohio, parts of New York, parts of northern Illinois, all of that stuff is under hundreds of feet of glacial till. And you can see She's standing on an erratic here. There's erratics there, there's an erratic there, and then there's also all this like sand and gravel and stuff. So this is all glacial till. And some of the features that we see are shown here. In fact, all the features we're going to talk about in this class are all shown here. So imagine we have a terminus. This is our retreating glacier's terminus here. And you got to imagine that at one time this whole thing was covered in ice and the terminus was kind of over here somewhere, let's say. And as the glacier retreats, it leaves behind glacial formations. Okay, so we tend not to get erosion on continental glaciers. I mean, we do to some extent, but it's actually more because continental ice sheets are moving over the land and they're altering that land. They might be eroding a bit of it on the bottom of the glacier, but what we're really interested in with continental ice sheets is the features they leave behind as they melt, based on the sediment and that was in there and the water that was in there and what the water does as the glacier is melting. So here we have something called a terminal moraine, and the terminal moraine would be the furthest, in the case of North America, the furthest south moraine that you see. So what's a moraine? Well, a moraine is, remember when I said a terminus in a stationary glacier isn't retreating nor is it advancing because the amount of melt and the amount of accumulation further up in the glacier is equal. And so the terminus is not going anywhere. It's just sitting there. As it sits there, remember, ice is continuing to flow forward towards the terminus at all times, and that's ice, debris, till, all that stuff. And so if the terminus is just sitting in one spot, all that material, like a conveyor belt, is being carried down the glacier and deposited in one spot. And that forms what we call the terminal moraine at the very farthest reach of the glacier. So there was no glaciation past here if this is the terminal moraine. Then the glacier starts to melt, and it's still depositing sediment, but it's depositing it evenly, right? Because the glacier is starting to retreat. And as it's retreating, it'll leave behind little icebergs that calve off and sit. And these are called kettle lakes. So this is ice that got abandoned by the glacier. It sat in one spot, creating a depression. And then when that glacier melted, it filled this up with water. This is like that devil's soup bowl that I mentioned in class. And so that's just depositing an even amount of till here. And we call that a ground moraine, right? So a ground moraine is where there's just an even amount of till being deposited as the glacier is retreating. Then the glacier might slow down again for a moment or completely stop. And once it does, it will continue to just deposit material in one spot as the terminus sits in just this one spot here. And we call that a recessional moraine. So every retreating glacial system on a continental ice sheet has a terminal moraine and then a series of recessional moraines as it's retreating back. Then we can also get drumlins here and eskers and kames and outwash plains and all sorts of other things that I will talk about coming up. So again, here's a moraine that I've already discussed in the continental text, right? There's a moraine there, there's a moraine there. But you can also get moraines on the sides because remember I mentioned that ice is flowing from the center of the glacier to the terminus mainly, but also to the sides. And so we can get terminal moraines, end moraines, lateral moraines, which are the side moraines, and then medial moraines. And that's commonly found. The medial and lateral moraines are really prevalent in these alpine glaciers. So here on the side here, you see this big long ridge that's not part of the rocky bit. This is all till, if you can see that. That would be a lateral moraine. So that's material being deposited on the side as it melts, right? Similar to these moraines here, but on the side of the glacier. And then sometimes the glacier has spaces in between it where it's depositing material, and you can think of that like two glaciers very close together in the valley, especially when they get a little bit smaller. And those are going to be depositing material between them because they're moving material this way and this way. And so you get this moraine that forms right up the center of the valley, and that's called a medial moraine. And you can see these also in, there's a bunch of these in Wisconsin, where two big glacial lobes, ice sheet lobes, were right next to each other, and so they were depositing material in between them. And so that's a medial moraine. And then again, as I say, any layer of till that's being deposited just as the glacier is retreating, that's a ground moraine. So here's a lateral moraine here. Here's a lateral moraine here. Here's the beginning of a recessional moraine here. And so that's the till that's built up around the glacier as it melts. Here's what that looks like once the glacier is gone. Okay, so here we've got, this is probably the terminal moraine or end moraine here, and then the glacier was depositing material, and then that curves around, and now this is probably a lateral moraine, and then there's probably lateral moraine material moving on the way all the way up here. And so some other features that we see in glacially depositional environments, we get as the glacier is melting and we get like pooling of water at the front of the glacier, it will begin to leave sediment, namely that glacial outwash, and that stuff will settle over the top of a ground moraine, and it'll create another layer of sediment of outwash material, and we call that an outwash plain. And so that sits right above the ground moraine here on top, and that's this lighter colored sediment that we have here. So that's the outwash plain. Again, you can have stranded blocks of ice that fill the depressions that they leave behind with water, and those form kettle lakes. Then you have these two features here. You have a drumlin, and that's a streamlined or parallel to the direction of ice, asymmetric hill composed of glacial till. And what's happening here is as the glacier was advancing, there might have been pockets at the bottom of the glacier that where there was no ice, right? And that fills with sediment as the glacier is moving across the land, and so it scoops it up into this kind of arrow shape. And then when it melts, it leaves that stuff behind in these big drumlins. And if you've ever been to Madison, Wisconsin, if you've ever driven to Wisconsin from here, you go through a place called the Drumlin Fields, and these are huge hills. I mean, they're hundreds of feet tall, and they build roads right through them. Sometimes there's towns perched on the tops of these. Sometimes, so they're not tiny by any stretch. We have drumlins here in Michigan too, but if you really want to see all of this stuff in action, just go drive around eastern Wisconsin. It's where most of this stuff was identified and named back in the day. It is kind of glacial feature 101, and they're very proud of it over there. I went to grad school in Wisconsin, and probably 75% of my my cohort was all studying glaciers. So also you can have these long tubes of water running through the bottom of a glacier, kind of like little river tunnels underneath the glacier, and that's going to pick up sediment and carry it and deposit it. And when you have that, you get something we call an esker. And that's these long sinuous ridges. We have one down by, what's that town? Just south of GR. Is that Cedar Springs? Caledonia. So down by Caledonia, I think, yeah, we have eskers down there. There's a bunch of eskers to the east of us. And so these are very common that you see on the outwash plain. Here's what a drumlin looks like in the wild, and you can see that it's asymmetric. It usually has a steeper side reaching the peak and then a long side here. Oftentimes the steeper side is more rounded, whereas the narrower side comes more to a point, but that's not always the case. Sometimes this side's more pointy and this side is more rounded, but you almost always have a steeper side and a shallower side. So that's the way to identify it. And the shallower side always points in the direction of ice flow. So in this picture, ice was flowing to the right. So the glacial ice was flowing in that direction. And this is what they look like on a topographic map. And you can see generally they're pointing down. So in this case, the ice is flowing to the south, right? And here we have that asymmetry. So it's steeper here and broader here, steeper up here, and broader moving down towards the direction of ice flow. But here, that's not so much the case. Here it looks a little more pointy in this direction, but you'll notice it's still steeper on this side. And here it looks more pointy towards that way, but it's still steeper on this side. So ice is always flowing in the direction of the less steep side of the drumlin. So keep that in mind. So taken all together, these are the major glacial depositional features. You've got you've got eskers rather, which are kind of underground rivers that deposit sediment. You have drumlin fields, which deposited sediment as the glacier was advancing. And then you have kames down here, which are little mounds of sediment that were formed when the ice was stagnant, not moving over this area, and water was moving through these little depressions in the stagnant ice and depositing sediment in these little hills here. And then again, you've got the terminal moraine, recessional moraines. We can have lateral moraines over here on the side sometimes. You've got kettle lakes. You've got outwash plains, etc. So what effect does this have on the soil? So glacial soils tend to be ubiquitous in the Midwest. They're everywhere. Most of Midwest soil is all glacial in origin. And it tends to be very fertile. And glacial outwash also forms the deposits that are the important groundwater aquifers in the Midwest. And outwash is also an important source of sand and gravel. We have lots of gravel mines here in Michigan. And so here, this isn't in Michigan, but this is what an outwash plain looked like. So this maybe is what Michigan looked like during the end of the last glaciation, minus some of the taller mountains here, but maybe not. And so you have this big, huge plain full of sand and gravel. Most of ours now is covered in grasslands, wetlands, or forest. But if you dig down, or if you stripped all the vegetation away from Michigan, this is what it would look like. And so if you're ever driving down the highway and you see a little subdivision around a lake, a little tiny lake, you see them everywhere. There's always like subdivisions built around these little lakes. Those lakes are old gravel mines because there's gravel mines all over the place in Michigan. So what they do is they mine that sand and gravel for mostly for road aggregate, what they build roads out of. And it's easier just to mine the gravel near the section of the road that you're building, and then you move on and you make a new gravel mine for the next section of road. It's much cheaper. So they tend to do it every like 2 to 10 miles. Anything over 15 miles, it's not cost effective to transport the gravel anymore. And so that's why you see all those little neighborhoods everywhere. And so those gravel mines are mining into this glacial outwash. So let's talk about some of the effects of glaciation on sea level. So glacial events and glacial periods over geologic history are one of the major causes of sea level rise and fall. So the amount of water taken up by the Pleistocene continental ice sheet, for example, dropped sea level about 100 meters. So that's 300 feet. Okay. So that's pretty significant. If you think about it, we're at 600 feet above sea level. So half of that would be maybe Virginia or North and South Carolina, a couple hundred miles wide they are. So you could imagine that at the glacial maximum during the Pleistocene, if sea level was dropped 100 feet, you can imagine the coast of North America over here extending out another, distance like this maybe, or even part of the continental shelf being exposed. And I want you to think about what would the impact be of a 6-meter rise, just 6-meter rise, okay, in sea level. And we'll talk about this a little more when we get to climate change. But a 6-meter rise in sea level, which is 20 feet, would look like this. All these red areas here would be completely covered in water. And that's just a 6-meter rise. Similarly, a 6-meter fall might expose, that same distance out into the coast. 100-meter rise or fall is a huge deal, right? Which is why the melting of the glaciers now in Antarctica and Greenland is such a big deal. Another really interesting thing, and this ties into plate tectonics a little bit. Glaciers also, when there's substantial amounts of ice, and during the glacial maximum during the Pleistocene, some of the ice in Canada and northern North America was almost a mile thick. So a ton of ice, right, on these ice sheets. And so what's that going to do to the crust that it's sitting on? Well, it's going to cause this kind of basin here where the ice is the heaviest. It's going to push that down. It's going to push this material away from it. So it's going to move that out. And it's going to push the crust in the center down into the mantle. So then, after all that ice has melted, material is going to begin to move back in this way on the sides and move up this way. And this is a process known as isostatic rebound. And this is where the glaciers have basically deformed the crust, and now it's rebounding back to its original form. And we have that here in Michigan. We're in a glacial basin. And well, we're in a tectonic basin that was exploited by the ice. And so Michigan is actually rebounding a few centimeters per year, I think. Don't quote me on that. But that means that the center of Michigan is slowly raising in elevation. And as that happens, that starts to change the way surface water is moving around. It's changing erosion patterns of rivers. It's changing directions of rivers. It's changing the way the Great Lakes look. All sorts of things due to this kind of rebound effect. Another effect of glaciation, and this should be somewhat familiar to us, is in the Great Lakes region, is the presence of large glacial lakes. And these would have formed as lobes of different continental ice sheets, were stationary as they were retreating and eventually just melted in place. And what happens is glaciers will tend to form those terminal end and lateral moraines, like I said, and then eventually when the glacier melts, those moraines can hold that water in, forming a lake. And in the western United States, we had a number of glacial lakes, comparable in size to a couple of the Great Lakes, at least Lake Erie, possibly Lake Huron when it comes to the Bonneville Flats here. And the evidence we have for that are Lake Missoula up here. We've got these lake shorelines that have these very characteristic erosional features that are associated with lakes. We also have the Bonneville Salt Flats. So you had one of the bigger glacial lakes down here, Lake Bonneville. That would have been a salty inland lake. And as it evaporated, it left behind these salt flats, which would be a mixture of halite and probably gypsum. And then we've got some of these white lake deposits down here. And many of these lakes, either their water made its way to the ocean in the case of Lake Missoula, which I'll talk about on the next slide, or that stuff seeped into the ground through infiltration and created some of the larger aquifers that we have in the western part of the continent. So some interesting features that we see associated with Lake Missoula are what we call the channeled scablands. And so if you can imagine, the ice sheet was up here, and that formed a glacial lake here, and that would have been dammed up by moraine and other material, even ice sometimes, ice blocks that calved off and didn't melt for whatever reason and trapped some of that water into the lake. And eventually that barrier, that kind of natural dam, was broken, and there were some estimates that the amount of water that we have in Lake Erie made its way to the Pacific Ocean through the Columbia River Gorge in roughly 2 weeks' time. The entire lake was drained. And so this was an incredibly violent event with lots and lots of water moving across the landscape, creating a few distinct features. These are ripple marks that we are familiar with our sedimentary environments chapter that we looked at. But these are, you'll notice down here we have structures. These are homes, and here's a little road. So these ripple marks are absolutely humongous. And so that means that this was a really, really large river. I mean, bigger than anything we have on the planet today. That would have made its way out through, again, the Columbia River Gorge, through Portland, and then out to the Pacific. We also have these pothole structures, and this is when large amounts of sediment and large, glacial erratics would have been washed down through this river system because it was so powerful. And that stuff gets stuck in these kind of areas of low depression, and you can imagine boulders just kind of swirling and rattling around here, and it actually digs this stuff out and creates these what we call potholes. So this is some evidence, and you can see here, this is the area that was swept by all the flooding as it moved through. So if you go back to the map on the previous slide, you'll see this kind of smoothed out area running through basically from northern Montana all the way to western Oregon. So there's been evidence of multiple stages of glaciation or multiple ice ages in the geologic record. And an ice age is considered any time that the global temperatures are 4 to 10 degrees Celsius cooler than they are now. So, like I said, we've had multiple ice ages dating all the way back to the Precambrian, so the Paleoproterozoic. And so there were different environmental effects acting on the Earth at different times, but we see a kind of similar process happening throughout geologic history. So something is causing the Earth to cool, and we'll talk about a few of those things now. So for global climate change, we see here from the Archean all the way up to the Cenozoic and up into the Quaternary, which is the present. You'll see here's a cold, and so these are warming periods. Here's the first large glaciation at the Paleoproterozoic about 2.4 billion years ago. And then we have a warming period and a cooling period, and then a couple of little colder periods here before another major cooling period. And then up here is where we get the Pleistocene, right? Also an ice age. You can see a much quicker back and forth between cooling and warming here. And this corresponds with global climate, obviously, and ice ages are somewhat rare. A greenhouse planet is more common in our history. And one thing to note is that humans evolved and are adapted to survive during colder climates. At their greatest extent during the Pleistocene, glaciers were at least 3 kilometers thick, so about 1.5 miles. They covered 3 times as much area as they do now. Like I said, about 30% of the Earth's landmass, and this is what that would have looked like during the last glacial maximum. And some of the biological evidence for cooling, we have deep sea sediment layers where different ocean organisms were building their shells, and they build their shells out of carbonate or silicate. And oftentimes, because those things have an oxygen in them, right? Like carbonate is a carbon with 2 oxygens, and a silicate is a silica with 4 oxygens. And we'll get different oxygen isotopes, which we talked about a little bit, and we'll talk about again during the absolute age dating portion of geologic time, where different isotopes are prevalent in the atmosphere at different times, and that has to do with how much water is being sequestered in glaciers or is available in the ocean. So we can take evidence from the fossilized shells of ancient organisms, and we can measure the oxygen 16 to oxygen 18 ratios, and we can figure out whether we were in an ice age or not, based on the comparison of those oxygens. And these guys are very sensitive to temperature as well. So based on the formation of the shells, we can also tell whether they formed in a cold water environment or a warm water environment. So these guys are found close to the equator during cooling, because everything sort of migrates closer to the equator where it's still fairly warm. And then during warming periods, we can find them in the fossil record at higher latitudes further away from the equator. Another species will coil predominantly right in warmer water, like this, and it will cool to the left in cooler water. So pretty interesting. That's a level of evidence that we have. And then we also have pollens. So how do we make climate inferences from pollen? Well, pollen collects in sediment, streams, lakes, swamps, and shallow marine environments, and different plants have different types of pollen, and different plants grow in different environments. So if we find pollen in the rock record for sort of plants that prefer warmer climates, if we find those the fossils of those fossilized pollen from those ferns and stuff higher up in latitude, we know that we were experiencing a warmer climate during that time. And if everything's sort of bunched up around the rocks that would have been at the equator at the time that this pollen was fossilized, we would know that we were in a time of cooling. And so that's about it. This is sort of the truncated version of glaciers. We're going to do a glacier lab in the upcoming week. But before we go, I would really suggest that you go into the lecture slides and you watch this little 6-minute video. There were some scientists up in Greenland changing out the batteries and whatnot on some monitoring cameras that they have, and they witnessed a major calving event where some icebergs on a glacier at the coast of southern Greenland, or I guess sort of southwestern Greenland, some icebergs about the size of the island of Manhattan calved off all at once, and they happened to be there filming a documentary of them changing the camera batteries in their monitoring camera, so they got the whole thing on film. It's really spectacular, and it's worth watching. So with that, I will leave you. I will see you all in lab, and I hope you enjoyed the glacier section, certainly pertinent to where we live here in the Midwest, and particularly in the Great Lakes region. Lots of glacial features everywhere, and next time you're on a road trip with family, you can point out all the moraines and eskers and drumlins that you drive through on your way to Indiana or Ohio. I don't know why you'd go to Ohio, and Chicago and places like that, because it's this whole area is covered in it. So have a great day, and I'll see you guys next time.